I want to peel back the curtain a little bit about these assumptions that we've been making about op amps. So we said that the current that flows into these terminals is exactly zero. And of course, in real life, that can't actually be the case. So in real life, there will be some, we'll call it an input resistance, which would connect these terminals together. And so in real life, there will actually be some current that flows in. So when we make an assumption, so the assumption that IP and IM are 0 is assuming that the input resistance is very large. So for a very, very large input resistance, the amount of current that flows into these terminals will be very, very small. And in real life, this is a pretty good assumption. So that zero current flows into these input terminals is a kind of a reasonable thing to use as far as first pass at analyzing an op-amp circuit. The second thing that we assumed is that the voltages, so that's Vm and Vp here, are equal. And that has to do with the actual behavior of the op-amp itself. So what this op-amp is actually doing, it's behaving as if it is a voltage-controlled voltage source, where there's some parameter A multiplied by the difference in voltage. So let's kind of dig into that a little bit. So the output voltage is V0 is A times Vp minus Vn, where A is called the open loop gain. And this is a parameter that you can look up in the datasheet for a particular op-amp that you're going to use. The values are typically fairly large. So you might have, so A in the vicinity of like 10 to the 4 or something like that would be a plausible, realistic value. So if this open loop gain is very large, then it means you only need a tiny difference in the input voltages. So if A is large, then a tiny difference in Vp and Vn will drive a large output voltage, V out. So this is the origin of this assumption that the input voltages are equal. We say, well, they're actually not exactly equal. There will be a slight tiny difference, but it only takes like a really, really tiny difference because this parameter A is just so large that we'll be able to achieve our output voltage even with a really, really tiny difference in the input voltages. So real life realistic parameter. So you could have, for instance, that the difference between the two pins could be in the vicinity of like 2 millivolts or something like that, approximately. And so that's pretty tiny in comparison with the other voltages that we would typically have in our system, or in comparison to the scale of the input voltages. And so as a result of that, therefore, our assumption about Vp being equal to Vm is a reasonable approximation. So Vp is equal to Vm is a reasonable approximation. Basically, if the open loop gain the open loop gain, that was our parameter A, is very large. So by making this assumption, what we're really saying is that this op-amp has a very large open loop gain. And so that gives us a little bit more of an insight into what's really going on inside of this op-amp. But for the purposes of doing the circuit analysis, we make the assumption of no current flowing into these terminals because we have very large equivalent resistance here, and also equal voltages across these pins because the op-amp circuit is achieving that via something like this voltage divider network that we see here.